Welcome to the review for test number 2. The test is scheduled for Tuesday, March 17th at our regular time in class. Bring your fully charged laptop or tablet. Just like before, we'll have the test available on Canvas.
So the first question involves rock weathering. And in this one, I'm asking, does rock weathering remove CO2 from the atmosphere? Is that true or false? It is true. Rock weathering does remove CO2 from the atmosphere because you'll remember that CO2 can combine with water to create a weak acid. And then that falls on the rocks on our planet and very slowly dissolves them. And this is a really slow part of the carbon cycle. And so those weathering products, those dissolved weathering products, can be transported by rivers all the way down to the oceans, where they combine with other chemical elements to form carbonates and silicate minerals, which eventually kind of drift down to the bottom of the ocean and form other types of rocks. So rocks that are based on quartz or limestone, like calcium carbonate. So yes, rock weathering does remove CO2 from the atmosphere. Photosynthesis also removes CO2 from the atmosphere. This is the process where plants use sunlight and water and CO2 to form carbon in their plant, in their roots and trunks and leaves. And so that's a process of removing CO2 from the atmosphere. And that's why we oftentimes choose to plant trees or reduce any kind of deforestation so that we can keep the CO2, remove the CO2 from the atmosphere by the growth of trees and other plants. The fraction of atmospheric oxygen has decreased in recent decades due to increasing combustion of fossil fuels. That one's also true. So think about combustion. I gave the example of a candle. So if you light a candle, but then you starve it of oxygen in some way by putting a little candle snuffer over it or something like that, or if you put a blanket over a fire or cover a campfire with soil or something like that, you're starving it of oxygen. And combustion can't occur without oxygen. But when combustion does occur, it uses that oxygen in that process and produces CO2, which goes into the atmosphere. So you're decreasing the atmospheric oxygen when you're increasing the combustion of fossil fuels. And it is a measurable amount, although it's not enough of like a decrease of oxygen so that, people don't feel that decrease physiologically. But there is a measurable decrease in atmospheric oxygen as the CO2 has increased due to burning of fossil fuels. Radiative forcing, which is a perturbation to the energy balance at the top of the atmosphere. So radiative forcing refers to a change in the top of the atmosphere energy balance. And remember, energy balance is the difference between the incoming energy and the outgoing energy at the top of the atmosphere. And you'll recall that the incoming energy is coming in from the sun, and the outgoing energy can either be reflected sunlight, which we call shortwave out, or it can be energy that was absorbed by the Earth and then re-emitted as long-wave energy, emitted from greenhouse gases, for instance, in the atmosphere, and that would be long-wave out. So outgoing can either be it is shortwave plus long-wave outgoing. The incoming is only solar radiation, shortwave. So radiative forcing refers to a change in the top of the atmosphere energy balance.
Which of the following are climate forcing mechanisms? Changes in carbon dioxide in the atmosphere, greenhouse gas, obviously. Changes in surface albedo, changes in Earth's orbit, or all of the answers listed here? Well, definitely CO2, because that's a greenhouse gas, and that's an important forcing. Changes in surface albedo definitely affect the outgoing shortwave radiation, and changes in Earth's orbit, although that happens on a very long time scale, that also is a climate forcing mechanism. So the answer is all of the answers listed here. Melting sea ice will cause what kind of a radiative forcing? Positive or negative? By decreasing what? Well, we know if you melt the sea ice, it's going to decrease the albedo, the surface albedo, because you're removing the bright sea ice and exposing the dark ocean. So, is that going to cause a positive radiative forcing or a negative radiative forcing? It is a positive radiative forcing. A positive radiative forcing heats things up. And if you're absorbing more solar radiation, then that's a positive radiative forcing caused by decreasing the surface albedo. The energy balance refers to the incoming energy minus the outgoing energy at the top of the atmosphere. So the answer is energy in minus energy out. Which of the following climate forcings cause cooling after an explosive volcanic eruption in the tropics? Solar variability, sulfate aerosols, volcanic ash, or increased cloudiness? The right answer is sulfate aerosols, because those are the things that are highly reflective, that get blasted up into the stratosphere and reflect sunlight away, which is a climate forcing. Cloudiness is only temporary. That's not really anything specifically associated with explosive volcanic eruptions. Volcanic ash also is temporary. Solar variability has nothing to do with volcanic eruptions, so the right answer is sulfate aerosols.
A positive feedback. What does a positive feedback do? Well, it doesn't dampen the initial forcing, it amplifies the initial forcing. So amplifies the initial forcing is the only correct answer here. A lot of times people get confused because they think a positive feedback always causes warming. A positive feedback can amplify a cooling effect. For instance, if we had some sort of atmospheric cooling that caused an increase in sea ice, an increase in glaciers, increase in snowpack, we'd have a big increase in the Earth albedo, and then that would increase the reflected energy away from the Earth. That would be more cooling, and more cooling then would cause the snowpack to increase, etc., and that would again amplify. So, and a positive feedback amplifies the initial forcing. A negative feedback dampens the initial forcing. So it sort of resets it back towards what it was. So you can have a perturbation that kind of pushes you out of that equilibrium, whether it's warming or cooling. But whatever that feedback is, that feedback then causes it to go back to more or less its original state. So a negative feedback dampens the initial forcing. Climate sensitivity describes the amount of warming relative to the total forcing. So if you have a forcing of, say, 1 watt per meter squared, but you end up, if you have predominantly positive feedbacks, then that means your climate sensitivity is probably pretty high. You might end up with an ultimate radiative forcing of, triple that. Maybe you've got 3 watts per meter squared, or even more than that, 10 watts per meter squared. So the amount of warming relative to the total forcing is the climate sensitivity, and the amount of warming is determined by whether or not the feedbacks are primarily positive or negative. Remember, if you have predominantly negative feedbacks, the climate sensitivity is very small. If you have a lot of mostly positive feedbacks, the climate sensitivity is going to be large. And here we go. A small climate sensitivity would tend to imply that the radiative forcing engages mostly negative feedbacks, right? So if it's negative feedbacks, it's going to kind of keep it at its kind of equilibrium state or push it back towards the equilibrium state. And so that means if it's not really changing, if the climate's not really changing in response to a particular radiative forcing, then it's not sensitive to that, and it's mainly a negative feedback in response to that particular forcing. All right, atmospheric rivers. They transport about 90% of the water vapor, and that water vapor is moving from the tropics to the high latitudes, and that's how that water vapor moves. And that water vapor is really important because it's not just water moving from the tropics towards the high latitudes, mainly in our oceans. It's the energy that that water carries with it because it's in the form of water vapor. And then when it condenses, it releases that latent energy, that latent heat that it was storing when it was vapor. So when it moves from vapor to liquid, it's releasing that energy. But that's why these storms are really energetic, really windy, and really, really wet, because they have a tropical source. And as you know, warm air holds more moisture. So ARs transport about 90% of the water vapor from the tropics to the high latitudes. Which of the following emission scenarios drives the greatest warming by the end of the 21st century? So take a look at the numbers at the end there, and you see 2.6, 8.5, 7.0, and 4.5. And you'll recall those numbers refer to essentially the radiative forcing. And so if you see 8.5, it's like, wow, that's a lot of radiative forcing. And you'll recall that SSP 5 is the one where the developing countries start gaining affluence, but they're doing that by depending on fossil fuels. And the developed countries are already using fossil fuels, and there's not a big switch over to renewables in that particular scenario. So in the SSP 5, 8.5, that is really a big increase in emissions, and more emissions are going to drive the greatest warming. So by the time at the end of the 21st century, we've got several degrees of warming in that particular scenario. The sunspot cycle explains the majority of temperature changes in the past 200 years. True or false? That one is definitely false. The sunspot cycle is a cycle, up, down, and it really does not have any significant trend, certainly not over the last 200 years. And so while you have a sunspot cycle on the order of maybe 11 years, that certainly does not explain the recent climate warming that we've seen over the past 200 years. So the answer to this one is false. Changes in obliquity, in the Earth's obliquity, change the seasonal distribution of incoming solar energy. So it changes how the solar energy is distributed between the northern hemisphere and the southern hemisphere by season, by winter and summer. Changes in the eccentricity of Earth's orbit might be suspected in climate changes on which timescale? That one would be 100,000 years. 11 years is sunspots. The others don't really have any relationship to Earth's orbit, so it's roughly 100,000 years or more. The negative phase of the Arctic Oscillation, the negative phase, that's the one where you get those big waves around the Arctic instead of the really tight zonal flow, keeping that cold Arctic air in. So it's responsible for cold air outbreaks over the middle of North America. The direct aerosol effect refers to, so remember the direct effect, it can be light-colored aerosols or dark-colored aerosols. So there's actually two correct answers to this question. So make sure you note that. Direct aerosol effect refers to increased albedo of the atmosphere if they're light-colored aerosols, and decreased atmospheric albedo by dark-colored aerosols. So the atmosphere would cool off with light-colored aerosols or reflecting aerosols, such as sulfate aerosols from volcanic eruptions. Decreased atmospheric albedo from dark-colored aerosols, that would be from, for instance, soot in the atmosphere, pollution, and that would increase the temperature of the atmosphere. for temperature and climate change, we need to think about not just the average temperature. We need to think about the maximum and the minimum temperatures, the daytime and the nighttime temperatures. And we also need to think about land versus ocean temperatures. And why is that? Because the average temperature doesn't tell us exactly what's going on. We need to know what the maximum temperature is by month, by day, by year, and the same for the minimum. And that's important for ecosystems and for infrastructure and for, just human adjustment. Daytime and nighttime temperatures, same thing. We call this the diurnal cycle, the day-night cycle. So the diurnal temperature changes. It, goes on a standard pattern. Daytime it's warmer, nighttime it's cooler. But it turns out that the minimum temperatures and the nighttime temperatures are rising faster than the maximum and daytime temperatures. And same thing for the average temperatures, rising faster than the average temperatures. Land temperatures are rising faster than ocean temperatures. But oceans cover 71% of the Earth's surface, so it's really important that we understand changes in all of these. And so the correct answer is all of these.
Sea level rise is primarily occurring due to which of the following? Melting sea ice? Nope. Melting sea ice does not cause sea level rise at all. Melting glaciers and ice sheets do contribute to sea level rise, but that's actually not the primary reason. Dissolution of CO2, dissolving CO2 in the oceans does not cause sea level rise. Increased precipitation? Nope, that's not causing it either. Thermal expansion of the warming oceans is the main cause of sea level rise at this time.
Which two of the following should be true about an emission scenario if it's going to be useful? Well, it needs to be plausible and it needs to be internally consistent. They can be qualitative and quantitative. They have to have numbers associated with them. They're not going to detail all possible change drivers in the climate, but they need to be internally consistent and plausible. So for instance, you wouldn't have SSP5, which is, where all the countries are burning fossil fuels, with an RCP of 2.6. That just wouldn't work, right? You wouldn't have a conservation scenario with a high fossil fuel burning either. Okay, which of the following factors is not important in creating the urban heat island effect? Well, we know impervious surfaces absorb less rainfall. That is true, and that's important. We know lower albedo surfaces absorb more heat. We know that buildings and cars create waste heat. All of those are important. The one that doesn't fit is the third one. Impervious surfaces promote ground storage of rainfall. No, it's the opposite of that. Impervious surfaces, that's the whole meaning of impervious. Impervious means water doesn't go through it. So if you have asphalt and concrete, water does not go through that. So those surfaces do the opposite of promoting ground storage of rainfall. They promote the runoff of that rainfall. So the soil below it is dry.
Changing from oil to solar energy would tend to what? Well, we know it would decrease emissions, right? If you're changing from oil to renewable solar. But in what way would that change? Would it decrease the energy intensity or would it decrease the carbon intensity? And in fact, the right answer is that it would decrease the carbon intensity because solar energy does not produce CO2. So the right answer is changing from oil to solar energy would tend to decrease emissions by decreasing carbon intensity.
In this question, I'm asking you to list and briefly describe the 4 major climate forcing mechanisms that I covered in class, in lecture. I want you to be specific and indicate if they are a positive or a negative radiative forcing. Greenhouse gases, so you would specifically identify several greenhouse gases that are important in climate change. For instance, CO2, methane, nitrous oxide, fluorinated gases. Some of these are natural, like CO2, methane, and nitrous oxide. Fluorinated gases are anthropogenic. but human activities are increasing CO2 and methane and nitrous oxide. All of these create a positive radiative forcing. Aerosols, as the next category, 90% of these are natural. Examples would be volcanic eruptions, wildfire smoke, marine salts, desert dust. And I want you to mention dark aerosols, which have a positive radiative forcing, but light aerosols, such as volcanic sulfate aerosols, have a negative radiative forcing, a cooling effect. Solar variability, an example of that would be sunspots on 11-year cycles or very long-term orbital variations. Sunspots are a positive radiative forcing. Orbital variations can be positive or negative or neither. They can just simply seasonally redistribute energy over the different hemispheres. Albedo change, for instance, changing land cover, deforestation is a negative forcing, or melting glaciers, snow, and sea ice that expose a darker substrate or darker ocean beneath, that is a positive forcing. In this question, I'm asking you to draw two climate feedback diagrams, a positive feedback and a negative feedback. Make sure each is properly labeled so it's clear to me, to the grader, what's happening in each case. You can use these two examples, or you can use other examples of your own, which would be even more interesting. So each of these, you need to indicate that there's a perturbation that sort of pushes the system out of equilibrium. So in the top one, the ice albedo feedback, the perturbation might be greenhouse gases, warming the atmosphere, creating more warming. That warms the atmospheric temperature. So there's that plus sign. Then that affects snow and ice. There's some melting. That's where there's that minus sign after it. Then there's a change in the surface albedo. The albedo decreases. Then there is more absorption of solar radiation, and so there's that plus sign leading towards the atmospheric temperature, which increases, and so on. So you can put a big plus sign in the middle of that cycle, of that feedback cycle, and to indicate that that's a positive feedback. A negative feedback here might be, for instance, the water vapor feedback. So again, perturbation, let's say again it's greenhouse warming, greenhouse gases. Warms the atmospheric temperature, so there's that plus sign. An atmosphere can hold more water vapor, so you increase the water vapor in the atmosphere. That allows more clouds to form, and so more cloudiness means that you have less absorption of solar radiation, so there's a minus sign just after that one because you're reflecting more solar radiation. When you're reflecting more solar radiation, now at this point, the atmospheric temperature is not going to go up again. So you can just kind of stop there. So that negative feedback, you want to have the minus sign in the middle of that feedback cycle. And this is about the IPAT relationship. And so I want you to show me that you understand the IPAT relationship by filling in the blanks to show how each term in this IPAT equation drives emissions. 1 point for each of these. So I stands for impact. And the impact that we're thinking about here is emissions. But we use the letter I because this actually comes from ecology. Anyways, so I is the impact and emissions are the impact that we're talking about specifically. P stands for population, and as population increases, emissions will increase. A stands for affluence, the wealth of a country. And as A increases, as affluence increases, emissions will also increase. T stands for technology, and that one has two components. And those two components are carbon intensity and energy intensity. And for extra credit, tell me what the units are of each of those. And fill in the blanks down below here using the answers from part D above. So as carbon intensity increases, what happens to emissions? They increase. That means you're using more fossil fuels in your technology, in your approach to making things. And the second one is as energy intensity increases, emissions will increase. So the units of carbon intensity are the amount of CO2 per unit of energy required to produce something. And the energy intensity is the amount of energy required per unit of wealth. In this case, we're using dollars of GDP, for instance, gross domestic product. Now, the energy units we typically use are British thermal units, abbreviated as BTUs. So energy intensity is the BTUs required to produce a dollar of some valuable item, widget, right? So it would be BTUs per dollar of GDP. And carbon intensity is the amount of CO2 emitted per unit, per BTU, per unit energy. So CO2 per BTU for carbon intensity, and BTUs per dollar of GDP for energy intensity. Okay, for this one, it's more about aerosols. I need you to answer all three parts of this question. Describe the direct effect of light-colored aerosols on climate. So, light-colored aerosols reflect light, thereby increasing the albedo of the atmosphere, reflecting more solar energy. They have a net cooling effect on the atmosphere. The direct effect of dark aerosols on climate is that they absorb light, thereby decreasing the albedo of the atmosphere, absorbing more solar radiation, and they have a warming effect on the atmosphere. It's called radiative heating. But the two indirect effects of aerosols on cloud are particularly interesting. First, aerosols act as little condensation nuclei that help create an abundance of very small water droplets in the clouds. And this abundance of small droplets do two things. They make the clouds brighter, more reflecting. They increase the cloud albedo. And the second thing is that these small water droplets, they're abundant, but they're too small to fall as rain. So they're just not heavy enough to overcome kind of the turbulence and the rising air effect that we often see associated with clouds. So the clouds tend to be longer lasting. They stick around longer. So they're brighter and they last longer. So these two indirect effects of aerosols on clouds have the effect of reflecting more solar radiation away. So they will also have a net cooling effect on the atmosphere. In this one, I'm asking you to draw and label a diagram of the urban heat island effect. You could use this one as a guideline. You can use a different urban heat island diagram if you choose. That's fine with me. But I just want to make sure that you get these four main contributing factors showing in your diagram and also listing them, okay? So lower albedo in the urban area, right? So the buildings, the pavement, all those things lower the albedo, which absorb more solar radiation. There's more waste heat associated with the heating and cooling processes of buildings, and also waste heat associated with vehicles, cars. There's less evapotranspiration, which has a nice cooling effect, simply because there's less vegetation cover on the ground. And there's less ground storage of rainfall, and the soils don't have the access to any sort of moisture that might fall on these impervious surfaces. So when you have rainfall on concrete or rainfall on parking lots, that rainfall is not absorbed into the soil and it can't be used for evapotranspiration. It simply runs off. And you also have more trapped heat and less airflow between the buildings. So you're not only trapping photons around the buildings and lowering the albedo, you're also trapping heat among these buildings. And you just don't have very good airflow between the buildings in these urban areas. So the second part of this question is at the bottom here. Briefly describe two strategies for reducing the urban heat island effect. Now, you don't have to be as constrained about water as we were in Las Vegas. You can talk about planting lots of trees and doing all kinds of things, misters and anything you want to include in there. Do this part yourself. You know the answers from the in-class activity, and that's up to you. In this one, I'm asking you to label a diagram of the Walker circulation. Be sure to include both the ocean and the atmosphere patterns and directions. So when I say the atmosphere pattern, by that I mean the trade winds, which are blowing from east to west. And you can see that you don't have to draw the thermocline. I'm not going to ask you to do that. But I do want you to indicate where the warm waters are and where the cool waters are. So the basic idea is, here is the Walker diagram, Walker circulation diagram, and I'd like you to be able to draw something similar to this. So the east side is Peru, like Lima, Peru, and the west side would be Darwin, Australia. Tahiti would be sort of in the middle. When the trade winds are strong, as they typically are in Walker circulation, they push the warm surface waters westward. So you end up with warm, wet system, a lot of convection, creating low pressure at the surface. And then on the east side, where you've pushed away that water, and so you have the cool water rising up from below to take its place. So you have cool water at the surface, and so the atmosphere is really kind of cooled off from below. And you end up with cool, dry, mostly high pressure, because that cooler surface, the air is not going to rise. And so it kind of sits there in high pressure. So that is the typical Walker circulation. Now, from the previous slide, the rest of this question, you have to answer this part as well. Briefly describe what happens to the Walker circulation when there is an El Nino event. So when there's an El Nino event, the trade winds are weakened. And those warm western Pacific waters, which had previously piled up in this western tropical Pacific, like around Darwin, Australia, they migrate eastward towards South America, back towards Lima, Peru, where they used to have cooler waters. So now the cooler waters in the eastern tropical Pacific are replaced by the warmer waters. And that causes a breakdown of this Walker circulation. You don't have that low pressure in the west and rising air and lots of precipitation. Now you've got drought conditions over in northern Australia around the Darwin region. And you've got really rainy conditions over by Lima, Peru, lots of flooding. So under normal conditions, you'd have high atmospheric pressure dominating in the Peruvian part on the east and low pressure dominating in the west over by Darwin, Australia. But because you've had this breakdown in the trade winds, with the warm pool migrating eastward, the pressures reverse. It gets very dry in the western tropical Pacific and very wet in the eastern tropical Pacific off the coast of Peru. And what happens when there's a La Nina? Well, it's basically like the Walker circulation on steroids. That Walker circulation pattern strengthens, the trade winds are even stronger, so you have even more warm waters piling up in the western tropical Pacific, more moisture, a lot more rainfall in that region. Ocean temperatures in the eastern Pacific are cooler than normal. Rains are very strong over the western Pacific, and conditions are much drier than normal in the eastern Pacific, so off the coast of Lima, Peru. And that is it for the test. All right, thanks.